For our final video in this series introducing chemical reactivity, we're going to look at the effect of something that we call atomic radius on the reactivity of metals as well as nonmetals. So to introduce the concept of atomic radius, we can go to the geometry definition of radius, that being the distance from the center of the circle to the edge at any point on the circle like this. And we can give this the short form R. So naturally, the short form for atomic radius can be AR for short. So if we take a look at the structure of lithium here, we can indicate what the atomic radius of lithium is by drawing a straight line from the center of lithium's nucleus, which is, of course, where all of the protons of the element are located. More on that significance later. And if we draw a line from the center of the nucleus to the edge of the valence shell, that being, of course, the shell of electrons that is farthest away from the nucleus, that is a measurement of the atomic radius. And if we compare lithium's atomic radius to the closely related element sodium, so again, we start by indicating the center of the nucleus here, and then we draw a straight line from the center of the nucleus to the edge of the valence shell here, so we can see that the atomic radius of lithium is smaller than the atomic radius of sodium, and this is obvious because sodium, unlike lithium, has 1, 2, 3 electron shells, whereas lithium only has 2. So the conclusion that we can reach here, which is of course relatively simple, the more energy levels, or the more electron shells an element has, the farther away its valence shell is going to be from the nucleus, and the larger the atomic radius is going to be. Now, what is the significance of this feature when it comes to chemical reactivity? Well, we can actually extrapolate a pretty easy explanation by just considering how metals and nonmetals react. For example, metals have the intrinsic desire to lose electrons because, again, for alkali metals like lithium and sodium, losing one valence electron is much easier than gaining 7. Now, if we consider what electrons are, that electrons are negatively charged, which has the opposite charge of the protons that are found within the nucleus, well, logically, sodium's electron, because sodium's electron is farther away from its nucleus than lithium's, that means that the attraction between sodium's valence electron and the nucleus is going to be weaker, because there is a greater distance between sodium's positive charge versus lithium's positive charge and its valence electron that we see here. Now, because sodium's valence electron is farther away from its nucleus, this means because the attraction is weaker, it must be easier for sodium to lose its valence electron compared to lithium that has a much closer distance to its positive charge and therefore is not as easy to remove. So the conclusion that we can reach about this is that metals are more likely to lose electrons if their valence electrons are farther away from their nucleus, because this means that electrons are farther away from the most important part of the nucleus, which is, of course, the protons, because of their positive charge that is able to attract to the negative charge of the valence electrons. So the conclusion that we can reach here is that because sodium has a larger atomic radius than lithium does, sodium is going to lose its electrons more easily than lithium and is therefore a more reactive metal, because metals always react with nonmetals by giving away their electrons to a nonmetal such as fluorine or chlorine. Now that we have this understanding of the relationship between atomic radius and the attractive force between the protons in the nucleus and the electrons in the valence shell, we can extrapolate a similar but opposite conclusion for the nonmetals on the periodic table, because of course nonmetals have the desire to gain electrons, especially for fluorine and chlorine, because gaining one valence electron is easier than losing 7. Now, if this is the case, if the goal of a nonmetal is to gain electrons, that must mean that the positive charge of a specific element is more important in terms of being able to attract electrons into its valence shell. So in this case, the opposite conclusion must be true, that because the atomic radius of fluorine is smaller than the atomic radius of chlorine, because again, chlorine has a third electron shell, whereas fluorine only has 2. This means that because fluorine's electrons are closer to the nucleus, the electrons are closer to the positively charged nucleus because of the protons, and therefore fluorine's electrons are harder to remove than chlorine's. And this is of course true with metals as well, but the consequence of this is the opposite in terms of reactivity. So nonmetals can gain electrons more easily if their valence electrons are closer to the nucleus, because of course the most important part of the nucleus in this case are the protons found within the nucleus, because protons are, of course, positively charged. And the closer the valence electrons are to the nucleus, the more attracted they are to it, and therefore, because the nucleus is closer to fluorine's valence shell than to chlorine's valence shell, fluorine is more easily able to gain a single electron than chlorine is, and this is why fluorine, as the nonmetal with the most valence electrons and with the smallest atomic radius, is actually the most reactive element on the entire periodic table, including being more reactive than chlorine. So what we have just summarized here is the relationship between distance between the nucleus and the valence shell, and how that relates to how attractive the nucleus is to the valence shell, and what this means in terms of metals and nonmetals being able to lose or gain electrons more easily. Now, if we extrapolate this to the entire periodic table here, we can say that as we go down the periodic table, we can say that atomic radius increases, and this is beneficial for metals because this means that the valence electrons get farther away from the nucleus, and as the valence electrons get farther away from the nucleus, they become easier to remove. So nonmetals become more reactive when the atomic radius increases, and then so we can conclude the downward direction in the case of metals corresponds to increasing chemical reactivity, because metals are more likely able to lose electrons. With nonmetals, of course, this is exactly the opposite, because in an upward direction, we can say that atomic radius decreases because, of course, they have fewer electron shells, meaning that their atomic radius gets smaller, and because nonmetals at the top of the periodic table have smaller atomic radii, let me just rewrite that more clearly. This means the valence electrons are much closer to the nucleus, and therefore more strongly attracted to the protons in the nucleus, and therefore nonmetals at the top of the periodic table are more likely to gain electrons than the nonmetals at the bottom of the periodic table, as we see here. This concludes our introductory series on chemical reactivity. So what you can do now to test your knowledge of the influence of both valence electrons as well as with atomic radius, below you can try the practice problems where you are given a pair of elements, and all that you need to do is select the element that you believe to be more reactive than the other and provide some sort of explanation that either connects to valence electrons or that connects to atomic radius in order to justify which of the two elements is the more reactive of the pair.